All right, we are in section 7.5. Section 7.5. 7.5, I think, is the dot product. Okay, 7.5 is the dot product. So section 7.5, the dot product. Make sure everything is good. Okay, the dot product. We're on page 743. Okay, so today we're talking about these vectors. So, given vectors u and v, dot product is, so we're going to say u dot v, so it's simply, literally a dot product. It's defined to be, and I need to give you what u and v are though. So u is a1, v1, and v, vector v, is a2, v2, the dot product of u and v is, so u dot v is defined to be a1 times a2 plus b1 times b2. That's what we mean by the dot product. Now, you're taking two vectors, u and v, and that definition, what I just wrote, is called, again, the dot product. And the dot product is a scalar, okay? This is a scalar. The result of the dot product is a scalar. So you're gonna get some number, is what we mean, okay? So with that in mind, example one. Example one. They say, given v equals 3, -7, vector v is 3, -7. They say vector w is -2, 5. Okay? They want us to find v dot w. Well, again, I just multiply corresponding coordinates. 3 times -2 plus -7 times 5. 3 times -2 is -6. -7 times 5 is -35. So I get -41. So the result of the dot product of vectors v and w gives me -41. Okay? So again, when I take the dot product, I wind up with a number. Then they did w dot v. Vector w dot vector v. Well, now I'm just going to reverse the order, so it'll be -2 times 3 plus 5 times -7. But it doesn't matter about the order. You still get -6 minus 35. Still get -41. So it turns out that the dot product is commutative. The order doesn't matter. The dot product is commutative. If I do it in the opposite order, I'll get the exact same answer. Okay? So that's one nice property of the dot product. C is v dotted with v. Well, v dotted with v just would mean I'd take -3, -7 and multiply it, or dot product with -3, with 3, -7. So I'll have 3 times 3 plus -7 times -7. That's 9. -7 times -7 is 49. That'll give me 58. Okay, that'll give me 58. Then they do the norm of v. What's the length of vector v? The norm of vector v, well, that's just the square root of the coordinate squared, so I'll take 3 squared plus -7 squared 3 squared is 9. Negative 7 squared is 49. That's the square root of 58. Well, what they're trying to show us is that v dotted with v was 58. The norm of v, the length of v, is square root of 58. So, if we're going to write this down in a minute, it turns out that the norm of v squared is the same thing as v dot v. That's going to turn out to be one of the properties of the dot product. If you take a vector and take the dot product of that vector with itself, that's equivalent to the length of that vector squared. So that's one of the properties of the dot product. Okay. All right. So on the next page, they give us some of these properties of the dot product. Okay. Number one, u, v, and w all vectors. They say that vector v dot vector w is the same thing as vector w dot vector v. Okay. In other words, the order doesn't matter. We saw that a moment ago. Number two, cv times w. cv dot w. So I'm taking the dot product. So c is a scalar. C is some number. Maybe it's 2 or maybe it's a 5. So a number times a vector dotted with another vector, well, that's the same thing as c times the dot product of the two vectors. Okay, again, vectors u, v, and w are vectors. C is a scalar, just a regular number. Third property, they say v dot w plus u. V dot w plus u. Well, that's v dot w plus v dot u. Okay? 4 is v dot v, the one I just showed you. You take a vector and dot it with itself. That's the same thing as the norm of v squared. That's the one we just talked about. 0 dot vector equals the 0 vector, that's a vector, 0, dotted with a vector v, well, that's equal to the 0 vector. Okay? Oh, no. Remember, the result of the dot product is a scalar, just a number, so that's equal to 0. So, 0 the vector, dotted with a vector v, any non-zero vector, is equal to the 0 scalar. Again, the result of the dot product is always a number, not a vector. So 0 the vector dotted with any vector v is equal to 0 the scalar, 0 the number. And finally, number 6, c times v dot w. C times v dot w, they say is equal to cv dot w. So I can multiply the scalar times v and then dot it with w. That's the same thing as taking v dot cw. All three of those are equivalent. I can put that c in front of the whole dot product, or put it just on the vector v, or put it just on the vector w. I'll get the same number every time I do that. So those are some properties of the dot product. Okay? Those are properties of the dot product. Well, I can also use this dot product idea to find the angle between two vectors. The angle between two vectors. Okay? This dot product can help me find the angle between two vectors. So given two vectors v and w, the angle between the two vectors theta is, well, they say that the cosine of theta is v dot w divided by normal vector v, normal vector w. Okay, so what we're imagining is we're imagining two vectors. Maybe this is vector B, maybe that's vector W, and we're trying to figure out how to measure that angle between the two vectors. That's kind of the situation we're talking about. Given two vectors that have the same initial point, okay, we want to be able to calculate the angle between the two vectors, and I can use that formula to do that, okay? That's going to be the formula I use to do that. So given the two vectors, I'll form the dot product of the two vectors, get a number, divide by the length of B, the length of W, and I'll have just a number here, and then the cosine of theta equals that number. And then I'll take the cosine inverse to actually get the angle theta. Okay? So with that in mind, example 2, they ask me to find the angle between the vectors. They give me vector V equals -4, 3, and they give me vector W equals -6, -2. And they say round to nearest tenth of a degree. Okay, round to the nearest tenth of a degree. Okay. Well, so to apply that formula, I've got to know the dot product of the two vectors. So let's go ahead and do that. V dot W. There's V and there's W. So -4 times -6 is 24. Plus, I'll have 3 times -2. So that's a positive 24. 3 times -2 is -6, so that's 18. So V dot W is 18. Well, I also need to know the length of vector V. That's the square root of the coordinate squared, so the square root of -4 squared plus 3 squared. That's 16 plus 9. Right? Square root of 25 or 5. And I need to know the length of vector W. Square root of the coordinate squared. So -6 squared plus -2 squared. Okay? -6 squared is 36, and that's 4. That's square root of 40. 40 is 4 times 10, so I'll get 2 square root of 10. 40 is, oh, let's write it out. 40 is square root of 4 times 10. I can split that up. The square root of the product is the product of the square roots. But the square root of 4 is 2 square root of 10. So that's where I was getting 2 square root of 10. So now I can put it all together. So the cosine of theta is equal to V dot W, norm of V, norm of W. Well, V dot W, we got 18. Norm of V, we got 5. Norm of W, we got 2 square root of 10. So just plug it in, okay? Well, 2 goes into 18, 9, so I can write this as 9 over 5 square root of 10, okay? And so cosine theta equals that, so that theta is the cosine inverse of this stuff. Make sure your calculator is in degrees, take the cosine inverse. Theta is approximately 55.3 degrees. Make sure your calculator is in degree mode. Take the cosine inverse of that, and that means that those two vectors sit at a 55.3 degree angle between them. Okay. All right. So that's how we find the angle between two vectors. Nothing hard about it. All right. Well, the next thing is orthogonal vectors. Orthogonal vectors. So what are orthogonal vectors? Well, when we talked about straight lines earlier in the course, we learned how to write equations of lines, all that stuff. Well, back in Math 171. You learn how to write equations of lines, all that kind of stuff. We learned when lines are perpendicular to each other or at a 90-degree angle to each other. So if I've got two straight lines in the plane, if they sit at a right angle to each other, they are perpendicular lines. Okay? Two lines excuse me, that sit at a right angle to each other are called perpendicular lines. Well, now we're talking about vectors. Two vectors that sit at a right angle to each other. Say this may be a vector u, this is vector v. We say that these are orthogonal. So orthogonal vectors are similar to perpendicular lines. We don't call vectors perpendicular to each other. We call vectors orthogonal to each other. But it's the same concept. Two vectors that are orthogonal to each other sit at a 90-degree angle from each other. Just as two lines that are perpendicular to each other would sit at a 90-degree angle to each other. And the last thing we're going to talk about with vectors is you're going to have maybe a plane, and we're going to think about the idea of a line that's just, you got a plane sitting, let's say the plane was the floor. Think about a straight line coming up from the floor at a right angle to the floor. This is called a vector perpendicular, well, a vector orthogonal to the plane. That's what we want to say. Vector, well, okay. They call it a vector normal to the plane. So it's just all this vector normal to the plane. So it's just different notations, okay? Different terminology, but it's all really the same concept. Orthogonal, normal, perpendicular, all pretty much mean the same thing. But when you're talking about perpendicular, that's going to be with respect to lines. When you talk about two things being orthogonal, that's going to be with respect to vectors. When you talk about a line being normal to a plane, that's going to be, or a line perpendicular to a plane, then we're going to use the term normal, okay? But they pretty much have the same meanings, okay? So here's our definition that we really need. So I'll put a couple of stars, really important. Two vectors are orthogonal to each other if u dot v equals 0. So whenever the dot product is 0, then the two vectors turn out to be orthogonal to each other. If any time you have two vectors and their dot product is 0, then those two vectors are orthogonal or normal to each other. Okay? So with that in mind, example 3. Example 3 says, determine if the given vectors are orthogonal. Determine if given vectors are orthogonal. So A, they give us v equals 3i minus 6j. Well, they wrote it in component form. 3i minus 6j. And they say w is 8i plus 4j. W is 8i plus 4j. So vector v was 3i minus 6j. Vector w was 8i plus 4j. So all I got to do is take the dot product. 3 times 8 is 24. Negative 6 times 4 is minus 24. So that equals 0. So are they orthogonal? Yes. Determine if the given vectors are orthogonal. Since their dot product is 0, yes, they're orthogonal to each other. B. B says vector S is 2i minus 5j. Vector S is 2i, negative 2i minus 5j. Vector S is negative 2i minus 5j, okay? Vector R is negative 4i plus 8j. Vector R, negative 4i plus 8j. Okay? I want to know are they orthogonal to each other. So I got to take the dot product. -2 times -4 is +8. -5 times a +8 is -40. That's -32. So no, they are not orthogonal to each other. They do not sit at a right angle to each other. Okay? So it's really easy. It's really easy to determine if two vectors are orthogonal or not. All I gotta do is check the dot product. The dot product is 0, they're orthogonal. If the dot product is not 0, they are not orthogonal. Okay. Well, the next thing we talk about on page 747. Okay. They talk about breaking vectors down into, decomposing vectors into orthogonal components. Decomposing vectors into orthogonal components. Okay? So suppose we have some point A, okay? And I've got some vector B. Okay? Got some point A, I've got this vector B. And I've got this vector W. Okay? So I've got V and W. Okay? They sit at some angle theta with respect to each other. We learned how to calculate theta if we want. So there's theta. Okay? And what I can think about is I can think about the what's called the projection of vector V onto vector W. So that would be this thing. So what we imagine is taking this vector V and projecting it down onto vector W. So this would project down to there. So, and we're going to look at so that's one component of the vector. And the other component of the vector, so this would be V1. V1, okay? And it is a vector, so I can't leave the hat there. And I can think about this as vector V2, okay? And remember how we added vectors. V1 plus V2 gives you V. So vector V is V1 plus V2. I can add these two orthogonal components, and these things sit at right angles to each other. Okay, so this vertical component sits at a right angle to the horizontal component. But if I add vector V1 and V2, that gives me vector V. Okay, now vector V1, again, it's called the projection of vector V onto vector W. Okay, so the way they write that mathematically, they say projection of vector V onto vector W. That's how they write that, okay? Now, I can think about that situation, but the other way I can think about this is, there's vector W, maybe vector V is at a obtuse angle with respect to vector W. Here, the angle theta is acute, between 0 and 90, but the angle could be obtuse. It could be bigger than 90, but less than 180. So if you got this situation, then now this would be vector V1, and it's still the projection of vector V onto vector W, all right? And this would be V2. So again, the vector V can be written in terms of its components. And again, these components are orthogonal to each other, okay? Vector V is equal to V1 plus V2, all right? So we can think about it in either one of those two situations. One where theta is acute, that's the first situation. But again, theta could be obtuse, and we'd have that second scenario, okay? But every vector can be broken down into its horizontal and its vertical components. And if you add the horizontal plus the vertical component, you get the original vector back, okay? All right, well, we really care about that projection of vector V onto vector W. And so that's the next thing that we want to talk about. we're gonna learn how to calculate the projection of one vector onto another. And that's gonna be really important. Later, when you get to calculus, that's gonna be important. When you do your engineering courses, that's gonna be important if you do engineering. So, decomposition of a vector into orthogonal vectors. Decomposition of a vector into orthogonal components. That's what we're doing when we do this projection mess. Okay? So U and V, given U and V, non-zero vectors. Okay? The vector projection of they say V onto W, okay, is given by they say just what we just said, projection of V onto W. The actual formula for it is going to turn out to be V dot W over the norm of W squared times vector W. Okay? And this is not a dot product, so I'm not going to put that there. But that stuff is more, because this is going to be a scalar, so all of this is going to turn out to be some number times vector W. So the projection of vector V onto vector W is a vector. And we saw that. Projection of V onto W was this horizontal component V1. That's a vector. So the result of the projection of vector V onto vector W is going to be one of the two orthogonal components. Okay? And they say number two, they say to decompose V, to decompose vector V into vectors V1 and V2, okay? Parallel, V1 and V2, parallel to W and orthogonal to W. Okay? They say that vector V1, we've already talked about this one, is the projection of vector V onto W, okay? Which was equal to this stuff. Okay? And vector V2 is going to turn out to be vector V minus vector V1. So I'll be able to calculate both of those two orthogonal components. V1 is going to be the projection of vector V onto vector W, which is V dot W over the norm of W squared times vector W. V2, since I'll know vector V and I'll know V1, V2 is going to be V minus V1. Because again, I got to remember that vector V is always going to be that horizontal component plus that vertical component. This is going to be the projection of V onto W, and that V2 is going to be this other one. But again, to get V2, I just solve for V2. If V equals V1 plus V2, then V2 would be V minus V1. So that's where this thing came from, was that formula. Okay? So this will allow me to calculate the projection of vector V, or to decompose rather, a vector into its two components. One component is the vector V1, which is the projection of vector V onto vector W. The other component will be that vertical component. So with that in mind, example 4. Example 4. Okay? They say given V equals negative 5, 4, so vector V, negative 5, 4. Vector W is 2, 4. They want me A, find the projection vector V onto vector W. Okay. That's part A. Well, according to that formula, this is V dot W, norm of W squared times W. So somewhere I gotta do V dot W. So take the dot product of these two vectors. Negative 5 times 2 is negative 10. 4 times 4 is plus 16. That's 6. I've also got to know the norm of vector W. Norm of vector W will be the square root of these components squared. That's 4 plus 16, square root of 20. Square root of 20 is 2, square root of 5. Okay? Square root of 20 will be 2, square root of 5. All right? So let's plug this stuff in. V dot W was 6. Norm of W squared means I take that stuff and I square it, so I got to be careful. And then times vector W. Okay? So let's simplify that a little bit. 2 squared of 5 squared. 2 squared gives me a 4. Square root of 5 squared gives me a 5 times W. Well, 6 is 2 goes into 6, 3. 2 goes into 2. 2 goes into 4, 2 rather, I'm sorry. So 6 over 4 reduces to 3 halves. So this is 3 tenths times W. So that's 3 tenths times vector W. W was 2 comma 4. So I just multiply 3 tenths times each one. 3 tenths times 2, comma, 3 tenths times 4. 2 goes into 10, 5, so 3 fifths. 4 and 10 have a common factor of 2. 2 goes into 4 twice, 2 goes into 10, 5, so I get 6 fifths. So, what I just figured out is the projection, vector V onto vector W is the vector 3 fifths, 6 fifths. So I just answered part A. 3 fifths, comma, 6 fifths. Okay? So we're at part B. All right. Part B says find V1 and V2. Find V1 and V2. Well, again, I gotta remember that vector V is gonna be V1 plus V2. And V1 is always gonna be that projection of vector V onto vector W. That's what we just found. So it's gonna be 3 fifths, 6 fifths. That's V1. And again, vector V2 is always gonna be vector V minus V1. Vector V was negative 5, 4. Negative 5, 4, sorry. Negative 5, comma 4, minus V1, but V1 is this stuff. So all I gotta do is subtract, right? And to subtract, you need a common denominator, which is 5. This is a 1. 1 goes into 5, 5. 5 times negative 5 is negative 25, right? Minus 3. All I'm doing is saying negative 5 minus 3 fifths. Take your calculator. Negative 5 minus 3 fifths would be negative 25 over 5 minus 3. And then I'm going to have to say 4 minus 6 fifths. Well, let me write it out a little more clear. So to subtract this vector from that vector, I'm going to have negative 5 minus 3 fifths. And then the 4 minus the 6 fifths. 4 minus 6 fifths. Okay? To do that subtraction, I need a common denominator. Negative 5 is the same thing as negative 25 over 5 minus 3 fifths. And then 4, I got to get a denominator of 5. 4 is 20 over 5 minus 6 over 5. So, negative 25 minus 3 is negative 28 over 5. 20 over 5 minus 6 over 5 is 14 over 5. This is vector V2. Okay? So I found V1, which was the projection of vector V onto VW, onto vector W. okay? Turned out to be negative 28 over 5, 14 over 5. No, that's V2. That's V2, there's V1. So we're done. Okay, that's V2, there's V1. All right. We're at example 5. We're at example 5. Make sure my recording is working properly. Okay. We're at example 5. And I'm going to refer you, I'm not going to write all this because it's very verbose. So read example 5, page 749. I want you to open up your book in Alex and read that problem. I'm not going to write that whole problem down. I'm going to draw the picture. I will read it, but I want you to open that thing up and read it. So we got this truck trying to go up a hill. There's the horizontal. This is a 10-degree angle. This is a unit vector U. Okay, and again, we're going to explain this in a moment. So we got a truck sitting here. Okay? And we got this force coming straight down. This is perpendicular to that. This is F2. This is F1. They sit at right angles. Okay? So again, that's vector F. So let's read the problem. Again, read this before you try to go through my work. So the situation is, they say a truck weighing 2,000 pounds is parked on a hill with a 10-degree incline. So there's a truck weighing 2,000 pounds parked on a hill with a 10-degree incline. It says, write the force vector F representing the weight of the truck through a single tire. So I'm imagining, I'm just calculating, since the truck weighs 2,000 pounds, and we're assuming 4 wheels on the truck, each wheel would weigh 500 pounds. A truck weighing 2,000 pounds is sitting on a ramp, all right? And I want to calculate the force on one wheel. So the truck sits on 4 wheels, 2,000 divided by 4 means that there's 500 pounds sitting on that one wheel, okay? Now, and again, that force is pointing straight down. So that's the negative 500 J. It's in the negative Y direction, so that's why only the J component is relevant, okay? So the force is negative 500 J. That's this vector right here. Now, that vector has 2 components. It has a component that is perpendicular to the hill, right? And then it has this component that's trying to push the truck back down the hill. All right? There's 2 components to this one force here. There's the force of gravity. This is the weight on the tires. And then this force pushing backwards, and it should be at the same angle as the hill. A little more accurate. So F1 would be the force trying to push the truck back down the hill. So this capital F, negative 500J, has 2 components. One is F2, that's the weight that's on the tire that's on the road. And then F1 is the force that's trying to push the truck down the hill. Those are the 2 components for the force. Okay? All right. So hopefully the picture makes sense. So, they say A, write the force vector F representing the weight of the truck. We have that, F equals negative 500 J through a single tire. Write F in terms of I and J. We did that, negative 500 J. The I component is 0, okay? And assume the weight truck is evenly distributed upon all 4 tires. So A, they just wanted me to write out the force, and it is negative 500 J. That's it. Part B. Part part B says that F1 and F2 be the components of F, parallel and perpendicular to the heel. So we have those two components, F1 and F2. Again, F1 is the component of the force that's trying to push the truck down the hill. F2 is that downward force at the tire that's resting on the ground, okay? So they want me in B to find the component vector F parallel to the heel, all right? And they want me to round to 1 decimal place, okay? Well, so F1, this F1, and this is a 10-degree angle. If that's 10 degrees, this turns out to be 10 degrees too, all right? Now, so F1 is nothing more than the projection of vector F onto this, and actually they say, okay, we're gonna let U be a unit vector in direction of the heel. Okay, U is a unit vector in the direction of the heel, right? Same direction of that heel that the truck's parked on, okay? And what I'm gonna find is I need to find F1. F1 is gonna be the projection of vector F onto vector U. F1 is going to be the projection of vector F onto vector U. Now, I need to be able to write what U is. If that's a 10-degree angle, then vector U would be, and if you remember, we learned how to do this in the last section, norm of U cosine theta I plus norm of U sine theta J. That's that component vector form that I learned in 7.4, I think it was, okay, the last section. But again, U is a unit vector. So unit vectors have length 1, so the norm of U is 1. So actually I can write this as 1 times cosine of theta, but theta is a 10-degree angle. And then norm of U is a 1 again, and so sine of theta is a 10-degree angle of J. So now I can actually write U explicitly. I can write U explicitly, right? So that's how I write U, okay? So again, F1 is the projection of vector F onto vector U. So just go to your formula for the projection of vector F onto vector U. That's going to be F dot U norm of U squared times vector U. That's the formula for the projection of vector F onto vector U, okay? So I've got to get F dot over U. So there's F, there's U. So F dot U, I just multiply component by component. Well, the I component is 0, so 0 times the cosine of 10 is 0. Then I multiply J components, negative 500 times the sine of 10 degrees. So this will be negative 500 sine of 10 degrees. And then the bottom, the norm of U squared, well, U was a unit vector, so the norm of U is 1. So I don't really need that. So I'm multiplying this stuff times vector U. But again, U is cosine 10 degrees, sine 10 degrees. Okay? So you can take your calculator and do that stuff. And you're going to get negative 85.5 I. And then you'll get minus 15.1 J. That's F1. And again, all you're doing is taking your calculator, negative 50 times the sine of 10 multiplied by that, that'll give you negative 85.5. Negative 50 sine, negative 500 sine of 10 degrees times that, that'll give you negative 15.1, and that's your J component. So there's F1, okay? There's F1, all right? Now, they ask you in part C says find the magnitude of the force required by the brakes on each wheel, okay? Find the magnitude of the force required by the brakes on each wheel to keep the truck from rolling down the hill, okay? So this is F1. F1 was this force right here. So that's the force of the truck that's trying to roll down the hill. Vector F1 is the force of the truck that's trying to roll down the hill. Vector F2 is the force that's on the tire that's on the road. But that vector F1 is that force that's pushing the truck down the hill. So I want to figure out what the brakes force needs. Now the brakes on the trucks are going to try to hold it against the hill, or hold it on the hill. So the brakes are working in the opposite direction of him. And for the truck to stay still, the brakes will have to negate that force. So it will have to be the opposite of that force. The brakes will have to exert a force that is completely opposite of that force. So my brake vector will be negative that vector, because that's the force that's trying to push the truck down the hill. So the brakes are going to have to be the negative of that. So the negative of that would be 85.8I plus 15.1J. That's going to be the force required to keep that truck from rolling down the hill. That's the force required to keep that truck from rolling down the hill. So that's example 4. Okay, that's example 4. And the next thing is work. How do we calculate work? And again, read this section. I'm not going to write everything, but read this section. We're on page 751. Page 751. So they talk about the definition of work on the top of page 751. So read that. Okay, read that on the top of 751. It says if D is the displacement of vector of an object and moving the object in a straight line, they say from points A to B under a constant force F, then the work W done is computed by work equals force times distance. Okay, work equals force times distance. So what they're saying is, suppose you have an object sitting here at point A, and you're going to move that object to here, point B. I want to take that object, pull it to there. Okay? Well, the displacement D is that distance from here to here. So D equals A to B, vector A to B. I'm moving the object from A to B, so my displacement is just the length of the vector AB. Okay? So they say the work done, I'm going to have to exert some force to pull that object. Okay? And they're saying that the work done is going to be the force dot the distance vector. The work done is going to be that force vector dot that displacement. Okay? Now, that's one way to write it, but they also say that work, and that's not a scalar. That's not a vector, that's a scalar, so it's just a W, it's not a vector. So the other way to write it is W equals the projection, they say, of the force vector onto that vector, the length of that, times the length of D. And thirdly, they say W equals, they say norm of F, norm of D, cosine of the angle of theta between them. Because what they're saying is, sometimes this force is in the direction of motion. That's when you get this one. But sometimes I'm pulling at an angle. Sometimes my force is like this. So suppose there's a box on the ground and I got a rope and I'm pulling from up here. So there's an angle theta between the direction I'm pulling and the motion, like this. So that's when you use this definition. Okay? Sometimes there's an angle between the force and the direction of motion, and that's when you'll use this version of the definition for work. Okay? Theta would be the angle between the direction of motion and the force being exerted on the object. So with all that in mind, example 7. With all that in mind, example 7. So again, read this, pause pause the video, read the problem clearly. Okay, pause your video, read this section on work, and read the problem clearly. I'm not gonna write all that. It says a man pushes a lawnmower 150 feet across the yard on a horizontal path. Okay, so you got a man pushing a lawnmower. Well, the lawnmower, there's a lawnmower right here, right? There's a handle on the lawnmower. He's gonna push that lawnmower 150 feet. Now again, the force is being exerted right here. The man standing here, he's pushing down on the lawnmower, it's gonna roll 150 feet. Okay? And they say he exerts a constant force of 30 pounds. So the norm of F is 30. They told me the strength of the force is 30 pounds. Okay? And they say the lawnmower is rolling at a 40-degree angle. That angle is 40 degrees. Okay? And they want to know, find the work done. Round to the nearest foot-pound. Find the work done and round to the nearest foot-pound. So what I have to imagine is, let's write it a little differently. So imagine if that force were here. So I've got to imagine there's the force. So the angle, if this is a 40-degree angle, right? Then what is this whole angle right here? Okay? If that's a 40-degree angle, then that whole angle is a 320-degree angle, the big angle. Okay? That's a 320-degree angle. All right? So again, I'm just going to apply my work definition. So I need to write, again, I'm going to push this lawnmower a total of 150 feet, right? So I know what D is. The norm of D is 150. I know what the angle is. The angle is 40 degrees. I know what the norm of F is. Norm of F is 30. So my work, norm of F, norm of D, cosine the angle between them. So the norm of F, they told me it was 30. The length of D, well, I know it's 150. And then the cosine, 40 degrees. Okay? The cosine of 40 degrees. Do that and calculate it 3447 foot-pounds. That'll be the work. So that's how I do those work problems. Okay? That's how we're going to do those work problems. Again, read this material. All right, that concludes section 7.5.